So that's kind of a requirement for these kind of mechanisms to be incentive compatible, is that the payment does not directly depend on the reported value, only on the allocation. And the other thing that was important was that the allocation was efficient. Okay. So essentially, if you have you cannot have a mechanism where the payment directly depends on the report and then still being sponsored true. So there is a theorem around this action. So let's move on to the sponsors, to the online advertising. So there's two types of online advertising. So one of them is called sponsor search, and that's the kind of ads that appear alongside search results engines, right? So you are, for example, in Google, and I'll show you some examples later. And sponsor search, there's an option that's being used. It's called the generalized second price option. Okay? It's not a victory option, but it's based somehow on this victory option idea. We'll look at how we could use VCG instead as an alternative option. So VCG is not used, but we could use VCG. And then we'll move on to a slightly different topic, which is ad exchanges. So ad exchanges are used for display advertising. So this is a different type of advertising. So the sponsor search is really when you go to Google, and you go to Bing, you go to Yahoo, you do a search, and then you get the search results and you get ads as well. Whereas display ads are the ads that you go to any other web page and you see some ads. These are kind of banners that are shown on the page, and these are called display ads. And there's different types of options that are used there. Okay, so we'll look at both of these kind of options. So, so in addition to, so how do websites have to make money, right? When they, especially when they provide a free service, the only way that they can really make money is through advertising somehow. Okay? So usually websites use this kind of display ads, so showing banners, and then if you set up your own website, you can make money quite easily in that way. Then there's another model, the sponsor search, and then referrals as well, so where you pay per transaction essentially. So there's different kind of ways that these advertisers work. So display ads are what's called pay per impression. So every time a banner is shown, the advertiser has to pay, right? So it's like the traditional style of advertising in newspapers, right? So you as an advertiser, you pay depending on how many newspapers are being sold, for example, right? Or in a magazine. So you pay per impression, essentially. Every time the ad is shown, you pay. So that's a kind of classical advertising which has been transferred to the online media, and it's called pay per impression, essentially. So impression is when you view the ad. Whereas sponsor search, as we'll see, is pay per click. So the advertiser only pays if someone clicks on the ad and doesn't pay otherwise. And then there's a third kind of model, which we won't go into, is pay per transaction, where the advertiser only has to pay if the user actually purchases something. Okay? And so the options are mostly widespread in the first, and that's why I focus on those kind of models. Okay, so this is what sponsor search looks like. Presume you've all seen this kind of pages. So you've got Google, you are typing in some sort of keywords, a combination of keywords, and then there's two kind of parts of the page, or really three, or more even nowadays. So there's the normal search results, which are called organic search results, and these are said to be unbiased. So things like algorithms such as PageRank are used to create those search results, right? So we won't go obviously into that because that's beyond the scope. So these are the unbiased search results, and you can go through several pages. Now, on the top and alongside, right, you can see it's created some really small letters, ads. Okay, these are called sponsored advertisements, and this is a very different system from the results from the unbiased results. So these are biased in the sense that advertisers will pay money to be displayed. Typically, the more you pay, the higher you come up in the ranking, right? And the top guy paid the most, and there's this auction behind the scene that's going on. And it's not quite highest bidder wins kind of thing, but it's close, but it's not quite that. And I'll explain exactly how it works. Okay, and then obviously let's see how do they pay, what do they pay, etc., etc. And we'll see that victory auction is kind of used in this space. Now there's really literally billions of pounds spent every year on these in this thing, and this is the main revenue stream of Google. I think more than 90% of the revenue of Google comes from this type of advertising on this particular, on the search page only. So as I said, so sponsor search, important thing to realize is that pay per click. So advertisers can bid for ads, and then say the highest bidder wins, more or less, as we'll see. But then, so whatever they bid, they don't pay until, say, you click on this ad, and then they pay. Okay? And these ads can be quite expensive sometimes. If you have, say, pharmaceutical product, sometimes can be up to £10. Okay? So that means that if you click on this ad, the advertiser is losing £10. Right? So it's quite a significant amount. Normally it's up to £1 or something like that, but these are significant amounts. Okay? So they're not just pence. Maybe 50 pence or things like that, or even a couple of pounds sometimes. So sponsored search, also known as keyword advertising or pay-per-click advertising because of the model, the payment model that is being used. And also it's called position auction because it's essentially you're determining through the auction not only who is shown, which advertiser is shown, but also their position. And obviously the position matters here. So the top position is the most important one because normally we scan, with our eyes, we scan the page from top to bottom. So we see the top adverts first. Okay? So that's why it's called position auction. So it's used, a similar mechanism is used by Google, Microsoft, and well, Yahoo is now using Google, I think, as well. So it's a similar mechanism, kind of auction that's being used in all cases. And it's shown alongside the organic search results, which are determined using the PageRank-based algorithm. But the ads themselves are determined by using sealed bid auctions. Okay. So the advertisers not only bid on individual keywords, but they actually bid on combinations of keywords. And they can bid different amounts on different combinations of keywords. Yes, and then this is kind of figures about how many kind of monthly searches there are in Google alone. So it's a big market. Okay. So when we look at thinking about, okay, when Google was thinking about, okay, how should we run this kind of auction, they were thinking, okay, the top slots are more likely to be clicked, and so these are more valuable. It's quite difficult for an advertiser to determine a value for each kind of slot because it depends on their position, right? So you could have two kind of models. You could have had a model where the advertiser pays for the impression, right? So impression meaning if the ad is shown, they pay, and it doesn't matter whether they clicked or not. Okay. But it's very hard for them to say, okay, how much am I willing to pay for being viewed here? And it depends on the position as well. So it's very difficult for someone to assess, okay, I want to be viewed, you know, I have a certain So it's very hard for an advertiser to determine, okay, what am I willing to pay? Well, it depends on which slot I'm in, right? So if I'm here, then I'm willing to pay less because I'm less chance to be clicked than if I'm at the top. So what the solution was, okay, let's, instead of having a pay-per-impression, have a pay-per-click model saying, okay, if you're clicked, if a user clicks on you, then it's fairly easy to determine your value for a click because you can track the users And you can determine, okay, for each click, this is how much on average I'm making a profit from each click, right? So it's for a given click, because there's no conditional being clicked, I know what my expected value is from a user that clicks on. Okay, so that's why actually the values is quite high, because once a user has clicked, I'm looking for coffee. Once a user has clicked on one of these ads, it's actually a high probability that I'm actually going through with the purchase. I'm interested already, right? I've already indicated my interest. Therefore, it's quite. It doesn't really depend then anymore. The position doesn't really influence anymore what the likelihood is that I'm going to make a purchase, given that I've already clicked on it. Okay. Whereas determining the value based on I have to take into account likelihood of clicks, which is very difficult because it depends on the position and many other factors, such as which other ads are shown as well. But for a given click, I can determine, okay, this is probably my expected value, my average value for a click, for a user, a specific user. And that's why Google decided to do pay-per-click instead of a pay-per-impression model for this kind of sponsor search result. Yeah. So the expected value is actually conditional on click is much more constant and easier to measure. Okay, that's why it's pay per click and not pay per impressions. Okay? Because so there's also this tracking that happens within the website, right? That you can actually track and say, okay, for a given keyword, once it's clicked, what will be the possibility of purchasing? So the expected value can be computed. Okay, so let's now think about let us put ourselves in Google's shoes and let's think. Okay, we want to design an auction for this because why not? I mean, we are auctioning off a scarce resource, which is in this case it's advertisement space, user attention, right? It's scarce. We have so many slots. There's a lot of demand. How do we settle that? Why not have an auction, right? That's what auctions are for, allocating scarce resources. Okay. So let's think about an auction, a kind of naive auction. So what happens is that each agent is asked to submit a value for the ad. So you could have an auction where you could submit a different value for each slot, right? Because you could have had an auction like that. Google decided not to do that. Probably too complicated for people to think about that, right? So they're allowed to send one value for a specific combination of keywords. Okay, so one possible bid, and then why we could and then let's think about sorting them. So suppose let's forget about the payments for now, but let's think, okay, who should get the top slot? Okay, so should it be the person with the highest value? Okay, so suppose we have a simple auction. Everyone reports their value for a specific user, and then the auctioneer sorts the slots in order of the value. Okay. Is this a good idea? Yes or no? Well, I think not, but it's not efficient. Why not? So if we only take into account the value.
Maybe you will misreport. You will give a big value, then you'll take it.
Okay. But that's fine, maybe. Maybe that could be but so what's wrong with that for the auctioneer's perspective? So maybe misreport, but maybe we could design an auction where truthful reporting is dominant strategy, perhaps. Even so, even if it's truthful, what could go wrong here? Maybe look at this from the search engine's perspective. Does this maximize search engine's revenue? Yeah.
I don't know how relevant the ad has to be to the keyword, but maybe the highest bidder is a porn website and you search for coffee and you don't want to show that. Something like that.
Yeah, exactly, maybe, yeah. That is getting towards it. So it could not be relevant. So what happens then if it's not relevant for the show? Yeah.
Nobody will use your search engine and you will lose
Yes,
users.
yes, that's one argument, yeah. Yeah, okay, so we want to show relevant stuff, not just anything. In a way we can say the value already encodes the relevance, but maybe it's not always the case. But what else? So that's kind of a long-term reputational effect. Is there more like immediate effect? That
Maybe if it's the same advertisement every time the user uses the search engine, and the search engine, then it will be some kind of boring. It will be more interesting if each time it's
Yeah.
different.
also true, could be true.
There's also, if the same advert gets shown to the same user several times and they clicked on it once, they're probably not going to click on it again if they see it again.
Right. Yeah, that's a good point actually. Actually, that's yeah. If it is the same user, yeah. But is there another reason that you put something else? Yeah.
If the same agents all hold the top positions, then any that would be lower than that essentially can't be used at all or get any revenue from it. So you want to switch those in every once in a while.
Yeah. That's also true. You will get that automatically in a way. I'll explain maybe later. But so if we look at it from the engine Google perspective, right? So suppose you get very high value bidders. They're all top ranked, right? But they're not. The ads are not relevant at all. What happens? Yeah.
The user's just going to ignore them.
Ignore them. Yeah. Which means not going to be clicked. Which means it's pay-per-click, no revenue for the Google. Okay? Because it's pay-per-click. So that's the key here. So if no one clicks these ads, Google's not going to make any money out of it. Because Google is getting the revenue from the advertiser. Okay, so and it's also not efficient in a sense because you're showing all these ads, but then no one's clicking on them. So actually, the kind of social welfare, if you will, of the user is not maximized, right? This is to do with the relevance in a sense. Okay. But yeah, so all these arguments are valid. But one of the things that is really standing out here is simply the profit from the from Google's perspective. So so the first auction actually that was designed by Yahoo was exactly this. Okay, so just use the value. And actually they had a first price auction, okay, with just the value. They started off with first price auction, and they saw that it didn't work properly. Okay, so so then a company called I think it was DoubleClick. I think they came up with another auction, and Google actually it was I think Google that came up with a variant that in addition to value, okay. We have what's called the quality. Okay? So the quality, so the value is what am I going to pay as an advertiser, right? My bid, essentially. The quality is something that is not reported by the advertiser, very important. It's something that the search engine determines. And so the quality really encodes the relevance of this ad. Okay? And it's you could see it as the probability of click. Okay. So what Google tries to do is tries to estimate the probability that a certain ad is going to be clicked. Now, how does it do that? It doesn't tell us. It's keeping this secret. Okay. So a bit like the PageRank algorithm, we know it's using PageRank, right, Google, but actually it's not using PageRank. It's using a variation of PageRank. Okay. And it's not in the other search, in the organic search result. And it's not telling us how to rank the page because otherwise you could easily abuse the algorithm, right? So it's keeping it secret. But what we know, there's several ingredients in this formula that they use to determine the quality. For example, it's the relevance of the ad shown, the text shown, how well it actually matches the keywords. The landing page, so the landing page is the page where if you click on the ad, it's the page where you actually go to. So it's the relevance of the landing page with respect to these keywords that have been typed in. But another big one is the it's called the click-through rate. The click-through is the historic likelihood that an ad was clicked. So that's the CTR, the click-through rate. So based on history, so if in the past people clicked on it, then they might click again. So that kind of thing. So these kind of ingredients are used to determine the relevance of the ad, so the probability of clicking. Now, so when we say, okay, we maximize, in a sense, the profit, but also we could see it as a social welfare. So the social welfare is essentially the expected value then. So the expected value is the value of the ad if it's clicked times the probability that it is clicked, right? So this is the expected value of an ad, and then we can maximize this. Right? So we can find, using the terminology we had last week, right? So we have all possible allocations, and we're trying to find the allocation that maximizes this product here, VI times QI. Okay. So it can get quite complex, especially if the click probability also depends on the position of the ad. Okay. But for the moment we kind of ignore that. Okay. So we assume that there's just simply click probability that's independent of the position, and then there's a value as well, and then we're trying to maximize this product, and then we're maximizing the sum over all the ads that are shown. Okay? Is that clear? So suppose you have here 3 ads are shown, then we have the sum of these 3 expected values, and we're trying to maximize that. Okay? So we will look at the position-dependent probabilities as well, but for the moment QI is simply the click probability independent of the position. So how do we do this? So remember in the combinatorial option, I said there's this problem because there's too many combinations, and here as well we have lots of advertisers. We have and we have maybe 10 slots that need to be auctioned off, but actually it's fairly trivial. So we can just simply sort all the ads according to their product of VI and QI. And then suppose we have K slots, so maybe 10 slots to advertise, then just rank them according to this product here. Okay? So that maximizes the social welfare, if we agree that this is a social welfare. Okay? And so the complexity, so obviously, as I said, so this happens on a millisecond basis. So you type in the keywords, you press search, and then these ads are shown and these auctions are run. It's not done beforehand, it's all done on the spot, using, obviously, agent technology. You can't just build by hand there. So computational kind of tractability is very important here. And the only operation that we really need to do is sort. Okay? And we know that we can do sort in n log k time. Okay? So that's just using an efficient sorting algorithm. That's you can do in n log k, where n is the number of ads and k is the number of available slots. Okay? So in the worst case, it's n log k kind of computational time, which is doable. Okay? So it's less than quadratic in time. So it's a very tractable approach. Okay, so this is how Google and other search engines sort their advertisements. Okay. So, but we haven't spoken about the payments yet. Okay, so this is the allocation, but how do they determine the payment? Now, we can't use the simple victory auction because the victory auction is only for one item. Okay, here we're auctioning off multiple items. We can't really use VCG because VCG, well, we could use VCG, actually we will, but so what Google chose is a kind of a concept based on the victory auction, the simple victory auction, and what they say is, okay, so if you remember the victory auction, one way to kind of interpret the victory auction or the second prize auction is say, okay, what should be the minimum amount I need to pay in order to still win the item? right? So if I'm my value is 100, but the second highest bid is 60, so the minimum I need to bid in order to win the item is 60 plus this bid increment. Okay, so that's the second highest price. So we can transfer that intuition in this kind of the same idea. So so payment Pj of ad in position j is equal to the minimum payment required to maintain that same position. Okay. So if we let's look at the situation where we don't have the quality. So let's ignore the quality for now. Then it's very simple. So suppose we have 3 slots. And the highest bidder kind of is willing to pay a value of 5 for this slot. I have 3, value of 1 here. Okay, if we didn't have the quality, it's very simple. This person will simply pay this bid, okay, and this person will simply pay this bid, and this person will pay. Maybe there's another 4th bidder here, and that's usually a reserve price that's being set in this position. Okay, so essentially, you're bidding, or your price is the kind of next highest bid, or the bid of the winner below you. Okay, so if we had 1 slot only, okay, that would be simply the victory option, right? And it would be incentive compatible. If we have multiple slots, okay, then it's not necessarily anymore incentive compatible. Okay. So let's see why that is. Okay. So, or maybe you can guess. Why is it not incentive compatible? So notice, first of all, that we have the same principle of the VCG option, where your bid or your payment does not really does not directly depend on your reported value. Okay. So this person pays 3, so 3 does not directly depend on the reported value. It just depends on your allocation, right? So we have the same principle that your payment does not depend on your report directly, only on your allocation, which does depend on your report. So why is this not incentive compatible then? How can we cheat?
Could the advertisers make a coalition and all agree to pay half as much?
Yeah, so the collusion is always an argument in auctions, but we always say we ignore the collusion fact. But yeah, that's true. But even without collusion, how could they benefit by cheating? Cheating in terms of misreporting, simply misreporting. Right. Any ideas? So I said before that this slot is most it's probably the most valuable slot, right? It's the top slot. Okay, but maybe this slot is less valuable than this slot, but maybe it's not so much less valuable. Okay, so suppose that these 3 slots, let's look at the extreme case, they are equally valuable. Okay? There's no difference between the slots. How could you benefit by cheating? Yeah, exactly. Yeah. Okay. So notice that this guy is paying 3. Yeah. So this one is paying 3. This one is paying 1. And this one's paying half. Okay. So they're paying different amounts.
Are they not sealed bid auctions? Or is
Yeah.
this because
Yeah, sealed bids.
how would you not risk not falling off the bottom and not getting if you kept on? Was this repeated?
So it's a good question. It's not repeated, but in a way it is repeated, right? Because you know what happened last time. Okay. So if it's not incentive compatible, you can start experimenting every time. Say, okay, what if I bid less than my value? Am I going to be better off? Okay. So you're going to start strategizing. You're going to start thinking, let me build a distribution of what the other bidders are doing. So yes, it's true that you don't know other people's values, right? But what we're looking at is the dominant strategy incentive compatibility, which means if something is dominant strategy incentive compatible, even if I did know the other people's values, so in a complete information game, it's still in my interest to be truthful. Okay, so that's kind of the most extreme case. So suppose this was repeated infinitely often, what would happen? But yeah, it's a good question. In reality, we don't really know what we're going to pay, and we might risk, if we bid too low, we might risk not being allocated at all. But we can experiment, right? Because this auction happens many times. So yeah. So in theory, at least, if we did know what these values were, we could obviously misreport, and we would be better off by, in this case, maybe reporting. What could we report? So we could report 1.1, yeah, for example, and then we would only have to pay 1. So this person could report 1.1, and then the payment would be, this one would be pushed to the bottom. No, hang on. Actually, nothing will happen. Actually, no. The best thing is for this person to bid something like 0.6, yeah, right, and then this person would be shifted to this slot here. This person, well, they would all be shifted up. Okay. But if it doesn't matter, right, this slot is much cheaper. Okay. So it depends a little bit. So if there's a large difference in the value of these different slots, then it does make sense to be truthful because you do want to have that top position. But if these slots are pretty much the same, then the next price auction is not incentive compatible anymore. Okay, but in a sense, because maybe of what you're saying, you don't exactly know what's going to be the price. So this auction still works in practice, even though it's not completely incentive compatible. So, but this was with looking at value only, but we don't have value only, so we have quality as well. Okay, but the principle is the same. So the principle is the payment is equal to the lowest amount I would have had to pay and still maintain the same position. So, okay, so now we have equality, right? And the quality is determined in the allocation. So when I'm determining the top 3 slots, then I have maybe agent 3 appearing here, who has the highest quality and value combination. Agent 5, V5, and maybe agent 1 appears here somewhere. Okay, so maybe we have this kind of order because this is maximized. Say this is maybe 7.5, 4.8, and 3.5. Okay. Actually, I'll have a worked example later. Okay. So could be now a solution that this person pays simply this price, and this person pays this price. So this one ends up paying 4.8, and this one ends up being 3.5, and this one, or maybe there's 1.5 here. Is that possible? Is that a good solution then? So let's take the same principle and just simply say, okay, this one pays this and this one pays that. Is that doable? Or something goes wrong here? Yeah.
Doesn't that give away the qualities of them, which is supposed to be?
It could give away, it would give away the quality of your competitor, not your own. Yeah, true. But is there another issue? So we are assuming here that, so we're paying 3.5, yeah. Well, we're assuming that the value here is at least 3.5, okay? But that's not necessarily the case. Okay? But we could have a very long value here of 2, okay? And the quality was maybe, well, I guess in this case that's not possible, but this is not a, let's see, it might not be a good example. So unless the, well, quality can sometimes be like an integer instead of a probability, okay? So let's make this nice round numbers. Okay. So here, suppose the value here was 2, and my quality was 4. Okay. Whereas here, maybe the value was maybe 3, well, yeah, maybe 4 and 1, right? So here, now at this point, I'm forcing these agents to pay 4, yes, but given conditional click, but his value was only 2. So notice that it is, pay per click, right? So this is, you're paying this 4 only when you clicked, but your value for given the click is only 2. Okay? So this is not good. Okay? So this is no longer individually rational in this case. Okay? So how can we fix that? Well, we have to somehow fix it with the qualities, right? We have to kind of take the qualities into account and correct for the qualities, essentially. So the question is, okay, so how do we get to the right payment then? Well, the thing is that the quality we can't change. This is determined by the search engine, but we can change our value, right? Our report. So V is our report. Now the question is, what's going to be our minimum report such that we maintain the same position, right? This is what Victory Auction does, right? What's the minimum report so that we still maintain the same position? Okay. Okay. So we have to solve an equation. Okay. So when do we start losing our position? Okay. When this product is less than 4. Yes. Or 4 or less, right? When this product is 4 or less, we start losing our position and we're going to go down. Okay, so how are we going to determine the value that is minimal so that we are still there? So we want to find this value minimum value that we need to report such that it's equal to this expected value of this other slot, okay? Right? So and that's, we can simply find that by dividing it by Q3. Okay? So this is how we determine the minimum value that we need to report in order to maintain the same position. Okay? So if this is if this was 4, so this was 4 here. Maybe this is 2 and 2 or something like that. Okay. So in this case, Q5 and V5 is 4. We already know that. Divided by Q3, which was 4. So instead of having to pay 4, actually, our value is payment is going to be 1. Okay. So it's also fair. So people with high quality actually end up paying a bit less in a sense, right? Because it's in the numerator, in the denominator there. So this is the payment function that is used in Google and in Bing.
So Google works out. They tell the people what their quality function is. So Google just tells them what the
payment is, and you
just
hope you
trust
trust them.
Google.
Yes. Yes. Yes, it's not very transparent at all. No. Yeah, so auditing is a problem. Okay. So the question is this option then strategy proof? Well, still no, right? The same argument I had before. So you can just say, to see this, put all the qualities to 1, and you can find the counterexample when it's not strategy proof. And that's how you can prove that it's not strategy proof. Okay. So we don't have this nice theoretical proof, but we can still say that it's kind of based on Victor option, and it seems to be working well in practice. Okay, so here is a little example. And okay, so I'll leave you to do this example, so let me go through it. So payment is, just to remind you, this is the payment rule. So you're looking at, so J is the agent allocated in slot J, right? So it's not agent J in this case, it's the agent that's allocated in slot J. So it's a little bit confusing, but yeah, so it's a position, J refers into position. So your payment is equal to the product of the value and quality of the person below you, right, divided by your own quality. Okay, so that's your payment. And see that it does not contain any of the agent's reports, because the quality is not something the agent reports. Okay, it's only the value Vj is reported by the agent. Now, the exercise for now is for you to, assuming we have only 2 slots. Okay, we have 3 agents competing for 2 slots. Who should get which allocation? What should their GSP? So this is called the GSP option, right? The generalized second price option. What's their GSP payments? Compute also the expected utility of the winners. So the expected utility is what? So expected utility is their utility times the probability of getting that utility. Okay? Obviously, they're only going to get the utility if they're clicked. So you have to take into account the probability of being clicked, and the payment is also only conditional on the click. So what is the expected utility of the winners? We already saw that in general it's not truth telling, but in this particular case, is it truth telling? If not, give an example where they can fail and see and maybe the utility of when they cheat. And then we're going to go also to the VCG option and say, okay, so the allocation will be the same because it's an efficient allocation, but the payments will be different, right? So what are going to be the payments if we, instead of doing the GSP, we use the VCG option, okay? So this is the assignment for now, for the next 15 minutes. So this includes kind of the break as well. So it's good timing actually. So have fun and let me know if there's any questions.
First, I have to find payment tree. The equation is like payment tree equal value 4 time quality 4, but there is no bidding 4. Only 2 slots, so you always can find it. Because of only 2 slots, so the value of this should be value the time will be should be 0.5, yeah, it will be 0.8, it will be 0.6, so the winner will be the 2. So the first slot will get about the 2, and the second will be the 3. So this is so bidder 1 will lost the option. So this will be 3 should be. So this will be okay, get it. Then you know.
beta 2 and the beta 3 because this time there's
Yeah.
0.4 or
You mean here, right?
yeah, this is the 2, win the bidding. So the slot, first slot should be the beta 2 and the second slot should be beta 3.
Yeah.
After that, you shall calculate the payment. So the payment of beta 2 is,
So we have to find the allocation first, and then we can
Yeah.
the payment. Okay.
yeah, then because J is the position J, so this is position 1. So you should, divide by position 2, the second position 2 you divide, then
So it's me. E3, 3, so the payment is
no. I think here you got the actually, Q2 should be 0.8, yeah? Then you, yes, then you divide by Q3.
Yeah, I put it
Q3,
wrong.
so yeah.
I put the wrong number. Sorry. So it equals.
It's not equal. So this one should, oh sorry, I do it wrong.
Because here you see 0.8 divided by the quantity of B2 is 0.4. It's about 2, right?
First one is 1.
That's called 1.
Because
No, you can
this is the allocation, we calculated. This is the point 8, then you,
this is 0.8, but you we have to divide by 0.4.
no divide by 0.4, 1 divided by 0.4, divide by, you can see here, divide by J. So this is your position. Actually you pay, it's about, between position 1, so you should pay the position 2 minus yours. Oh, sorry. I do it wrong.
Because we have to count, because it's a second,
Yeah, so
so
sorry. So it should be the payment should be Q3 divided by Q2. It should be Q2 is 1.5. Yeah, first one should be 1.5. So this one should be
Oh yeah.
V1 Q1 divided by Q3.
Yeah.
Divided by Q3, it should be how much Q3 is 2 over 3.
Oh, sorry, I counted the wrong thing. It's 1? When
2.
B3. Yeah, 2. It's weird.
Pay more than
No,
cost.
this is winner.
Yeah, winner, better to
This
pay.
is second winner. And utility is 1.5. Oh, that's right. Utility is 0.5.
The utility is utility of
0.5. Right.
utility of beta 2. Beta 2 should be the actual pay.
Because we have to find the profits, right? Because the Google we pay for beta 2 is 1.5, and the value
this is the report value. This is the actual report value. This should be the actual pay. So it should be actually pay minus report value minus your actual pay. So the utility should be minus. The first one should be minus 25. Yeah. When you win an auction, when you win, your utility is your report minus the actual pay. Yeah. If you bid 1 million for just the 1 pound, so your utility will be 1 million minus 1.
But it's
It's like that, or the actual payment. I think it's that. So this is a report. So it's a report. So the utility of bidder 2 is minus 0.5. So the utility of bidder 3 should be 1.
a bit to wow.
See, this is
Oh yeah. Okay.
the report is the value.
Here you mean here.
Oh, sorry.
0.5. Because the value is 2.
Oh, sorry, 2. Sorry. 2 minus, yeah, 4.5.
1.5. Yeah.
4.5.
So it's 3.
It should be for
I think it's not too terrible. Because the bidder use hard.
no, it's not choose because you should calculate your quality. When your quality is high, you bid less. It's like this kind of stuff. But you should find your minimum value, like report value. Yeah, you should find your something like that. But all the reports and all quality, this kind of value is available. Is visible for all the bidder or not. This will be a problem.
So it's
available.
minimum value.
Yeah, minimum value. I think it's that one.
There's something wrong. Because payment, payment calculated function equals J plus 1.
Yeah, that's right.
But it's how is calculated.
Yeah. This is actually the same. It's the same. It's the same. Yeah, this is the state of your minimum reported value. So it's actually you want to pay, everyone wants to pay the less. Because maybe someone in this report, maybe business in this report is very high value or very less value. So, yeah, so I think should be two, yeah.
Yeah. And utility, I think minus 0.5 and minus 1.
It's payments minus.
Because it's a payment that you get from but our value is
Our value minus this one.
So that should never be.
So this is your utility. So using this value.
but it should be minus. Because our app is equal to but we get only one.
Oh, we
It's
actually
meaning-
pay two.
Yeah.
We actually pay two, but the actual value is 1.5. So it's 1.5 minus 2. Might be.
Because we lose the profit.
Yeah, I think in this way, yes. Right. So this is the report value. So this is the value in your side, on your side. So this is the value. So the payment is the value of the Google side. Okay, yeah. So this one should be 2 minus 3.
I'm not sure. I think it's could be.
Could be.
What about VCG? I forgot how to calculate VCG.
VCG is about, the use allocation should be this one. This one should be the allocation. So we shall calculate the payment. Yeah. The money. So the money should be the social welfare should be 3.1. So the VCG then you find allocation. Allocation should be beta 2 and beta 3. So the maximum we should have the maximum social welfare should be should be this one at this one, yeah. The 3.5. So
You're saying they want to have it.
the first you see the last should be 3.5 minus, so if you this should be 2 plus 1.5 and 1.5 plus 2 should be the same. I'm not sure. I forgot. Transfer is the rest of the actual money, the payment should be the payment for the rest. Yeah. Oh, this is the utility. Oh, okay, I got it. The total utility should be. So it depends on the first one is the utility, this one is this is the actual payment. So this should be right, but this one, I don't know this one is yes or no. Yes. So if this is right, so it should be. So the other utility should be minus 1, minus 0. This should be 0.5. This should be 1.0.
This is for beta 2 for beta.
Yeah, this is beta 2. Beta 2, this is beta 3. So the maximum social welfare should be 3.9. the utility is because you calculate the utility is minus 1.
I forgot the equation.
Equation is about
Number.
equation is about the
Utility
utility.
of them.
No, it's about the utility because it's first of all you find the maximum social welfare, then you find the allocation, data allocation, the maximum social welfare allocation. Yes. After that, you shall find out except this data, all the other utilities, added together, then plus all the money, all the payment is exactly the bidder two, except the bidder two.
So the application fare is about the payment.
No, it's about the first function for utility. Second one is about the money. It should be added together, but yeah, the first one is this is the money, and the first one is about so I think this one it should be this.
Yeah.
So it should be the utility. Utility is, for example, this is beta I. This is beta I, yeah. So this should be the maximum utility of the allocation. So except minus beta i's utility. Then you find this one. This is all the money you should pay for this allocation except beta I as well. So this should be the utility minus beta i's utility. This should be all the money minus all the money for this allocation minus beta i's payment. So it should be the result. So this should be the utility. So because the allocation is beta 2 or beta 3, so the only utility except the beta 3 should be except the beta 2 should be the utility of beta 3. Beta 3 plus the payment of beta 3 should be the BCG value for beta 2. Yeah. But this one is the same. So this is the utility of beta 2 plus the payment of beta 2. So it should be, I don't know this utility is not a lot.
Yeah.
So this is the problem. So this is minus 1 plus 1.5. This is actually payment.
No, what's a minute?
How many have you done already? Has anyone started the last one? Starting?
Yeah, it should be like that.
Yeah. Can't remember that.
It's the same.
Ah, yes.
How to calculate the utility? It's the problem.
Yeah, that means right down there.
And also, when we do the BCG, the value when we calculate the transfer, is that just V or is it V times Q?
V times Q, yeah. So the VCG, just to give you a hint, is no longer pay-per-click. Yes. You have to yeah, so you can't do VCG with pay-per-click.
Okay.
So it's a value fixed payment, no matter what, whether you click or not. I guess that's the goal. But yeah, so there's many ways in which to write the transfers, right? But the transfers for the VCG were essentially the social welfare minus the expected utility of agent I. So in this case, it's PI QI. Minus plus minus social welfare.
So the
without
utility
I.
should be this.
One equation.
actually, it's not actually the,
It's not utility.
it's not utility at all. Social media, for example, this is the, for example, this is, you know, YouTube. So in this allocation, the social welfare will be, this is the social welfare. Yeah, after the utility added together, this is social welfare.
feel free
知道好，我他妈感觉我有天天错了，我不知道他。好像不对，我有点不是往那个。根本都是算对了，但是但是有些是有服务的，所以天天就是说我现在估价是2块钱，但是实际我的 payment 的算法是1块5，那我这个作业是我的估价，是我的 payment，还是质量的，那质量跟你有什么关系？我只是给2块钱，如果保质，如果质量不好，质量差，我是第二个月报价的话，还是如果叫5块，那我的有这个是按5块5还是5块5这2块？估价就是我报价报的，他那个算法算出来，我应该是1块钱。
That's what we expect from the evening. Is it per person that goes through? That's expected to for EPA per person. We look at just people that which is that then is expected utility per person. Which that makes sense. That's in the social analysis. So it's not the time machine.
Let's change or not?
Yeah.
So if we calculate the BCG, we should ignore the quality. Because BCG in that equation we don't have setting for the quality.
Sorry.
In the first one, we only count the ones that related to the source.
Yes. Yeah. Exactly. Yeah. So sorry. Yes. Okay. what the answers are. If you came up with what answers you came up with. So I should mention perhaps this was actually an exam question. A bit modified, but okay. So let's have a look. So the first bit should be fairly straightforward, I hope. So let's look at the assuming 2 slots. So what are the allocations and what are the payments? So who gets which slot? Yep. So you have beta 2 in the first slot, maybe agent 2, and agent 3 gets the second slot. Yeah. Okay. Right, and then agent 1 does not get any slot. Okay. So what is the payment for agent 2?
1.5, 1.5.
1.5. And agent 2?
2.
And agent 3?
2.
2. Yeah. Okay. Yeah. Okay. And agent 1, how much does agent 1 pay? Trick question always. 0, okay. Yeah. So agent 1 pays 0. You don't get there's options where even the winners have to even people who not win have to pay something. There are these kind of options. Okay. So now the next bit is a little bit more tricky, the expected utility. It's not kind of obvious because we really didn't go into too much detail what the expected utility is in this context, right? But you have to be able to kind of infer from your knowledge what I mean by that in some sense. But okay, that's why we're practicing. So what is the expected utility for agent 2? Expected utility. So the expected utility is essentially the expected value minus expected payment, right? So any other solution for that?
Yeah, it's not very much. It should be.
Yeah.
Should it then be V2 times Q2 minus P2 times Q2?
Yep. So, no, sorry, not V2, no? Yes, yeah, V2 times Q2, yeah, minus the payment, yeah. So it's 1.5, yeah, 1.5 times Q2. Yeah. Okay. So one way to write it a bit shorter. So you can have, so Q2 is the probability of being clicked, right? If he's not clicked, well, if he's clicked, then his utility is equal to V2 minus his payment, is 1.5. Okay. If he's not clicked, then his utility is 0. Okay. So this is the expected utility, right, of play agent 2. The expected utility of agent 3. So how much is it actually? Both of them. So this is 4 times 0.5 is 0.2, yeah. Okay, and so this one will be Q3 times V3 minus 2.0. Okay, and that's 0.2 times 3 minus 2, 1. Yeah. Okay. Correct. That's 1.2. I think that's a coincidence. Okay. So now the auction truth telling? What do you think? In this case, right? So in this particular instance. Or in other words, have you found an example where a bidder, by misreporting, can get a higher expect utility in this setting, assuming complete information.
If B2 goes lower,
Yeah. Yeah, go ahead, Shane.
it's slot 2,
Yeah.
the fact falling out when he was better.
Okay. So let's investigate that possibility. So you're thinking, yeah. So beat agent 2, beat the 2. If he wins the second slot instead of the first one, he's better off. Okay, let's have a look. So what would, if agent 2 would get the second slot, what would be his payment? Maybe Felix?
I think he has a utility of 0.4 spec and
Point one?
I think I've got
One.
I think I've got one.
Yes, yeah, exactly. Okay. So obviously, if we move agent, I think they are correct. Yeah. So if you move agent 2 to agent to the second slot, his payment is not going to be 2, right? So you have to recalculate his payment. Okay. So that's then. Oh, sorry, it's not going to be 2. So the payment is going to be going to be with the 1, so 0.4 divided by 0.4. Okay, so this is equal to V1 Q1 divided by Q2. Yeah. So it's 0.4 is 1. Yeah, payment is 1. Then his expected utility of agent 2 is equal to still Q2 times, but now his value is still 2, but now his payment is 1. So yeah, so now it's 0.4 times 1, it's 0.4. Okay, so he can, but misreporting has a utility of 0.4, whereas with reporting truthfully has a utility of 0.2, and therefore he can benefit by misreporting. Okay, so this is clear. And then the final bit, now compute using the VCG mechanism. So now we are back into last week's lectures, and I like to do that. I like to mix and match the various topics together. So let's see whether we can transfer the idea of VCG here. Now VCG is a little bit tricky here because we've talked about pay-per-click. VCG doesn't do pay-per-click as such. There is a version of VCG that does pay-per-click, but that's not VCG. So I've written a couple of papers about it. It's sometimes called execution contingent VCG, but it's in this case we'll just look at normal VCG. Then, so what do we get? So, any ideas? Anyone want to? Maybe we didn't get that far. So with VCG, what was the idea? So we take the social welfare of the efficient allocation, but exclude the welfare essentially of agent I. Okay, now in this case, we look at the expected utility. So we take the multiplication of VI QI. So here we've got so the social welfare, the total social welfare, as we know, it's 0.8 plus 0.6. Okay, that's the social welfare of the efficient allocation. Okay. Now, if we first take beta 2, so we exclude his social welfare, so that's 0.6, and then we deduct. So this is the social welfare of everyone else, and then we recalculate the optimal allocation when agent 2 is excluded from the market. So in that case, agent 3 and 1 get allocated a slot, right? So the social welfare, if we exclude agent 2 from the market, is going to be 0.6 plus 0.4. Okay. So and we have minus 0.4.
This is for player 2's transfer.
Yes. So this is T2. Yep. And then T3 is equal to, so then now we're excluding T3 from the social welfare, so we are left with 0.8. Okay, and then we are recalculating the social welfare without the optimal allocation if we exclude agent 3 from the market. So then in that case, bidder 1 and 2 gets allocated. So we have 0.8 again and 0.4. Okay, this is minus 0.4 as well. So the payments are the same. Okay, now this is not a coincidence. Okay, essentially, in this case, I don't know if you've noticed, but we've treated slots 1 and 2 the same. Okay, so because yes, we have equality, but equality, the big probability, does not depend on the position of the slots in this case, in our simple model. And we're going to look at more complicated models later. Okay, so in this very simple model, the click probability does not depend on the slot, therefore the slots are the same. Now we are auctioning off 2 equal slots, therefore they are all the same. So in VGG, we'll then always give the same value to those slots. Okay? So the same payment for those slots, if they're identical. Okay? That's the property of VGG. In fact, if we have, say, 3 slots that we're auctioning off, if we had the normal value, so instead of expected value, but or expected value, it doesn't really matter. But the price is equal to n plus 1 highest price in that case. So remember, if we have 1 slot, the VCG auction becomes the second price auction, right? The victory auction. If we have n slots, the VCG auction becomes the n plus 1 highest auction. Okay, and we can see that n plus 1 in this case, right, is the expected value of bidder 1, right? That's n plus 1. This the third price auction in this case is 0.4. Okay, so that's just a kind of an aside in a sense. So this is when we have identical slots and every bidder only wants 1 slot. Okay, then this n plus 1 auction is equal to the victory auction. If you want multiple slots, if there's multiple slots, that's not the case. Yeah.
Who will then get the allocation now that they all have the same transfer?
Still the same allocation. So the social welfare is the same. The social welfare of the efficient allocation. So still you get the bidder 2 and 3. That doesn't change because we were already maximizing that. Okay. So the VCG always looks at the optimal. Any other questions so far? So now this is the simple bit. Okay. Now it gets more complicated. Okay. So far the click probability only depends on the quality but not on the position. Now we already saw that that's not realistic, but that's what Google does. It's fine. In a sense, you know, the highest bidder does pay less. You know, so the high slot is generally more expensive than the other slots. So it is kind of encoded in the payment in a sense. But let's model this a little bit more in detail. Okay, so we could have an additional variable, lambda, called lambda j, which is the probability that the user views the added position j. Okay, so the quality here is you could have a different kind of interpretation. So the quality is if the user views the ad, ends up looking at it, right? You can do some eye tracking kind of things. If the user views the ad, then he will click with probability QI, but the probability that he actually views the ad in the first place is given by this probability lambda j. Okay? So, and normally, if you have like a, in most cases, you would scan the page from top to bottom, so the lambda j will be higher for the top positions. Okay, so you will have a high probability of viewing ad j. So then, in this new model, we can say that the probability that the ad is clicked is the product of the quality and this lambda value, where the quality depends on the ad that is shown, but is position independent, and the lambda only depends on the position and not on the ad. Okay, so AJ here is the ad in position J, whereas then lambda depends only on J. Okay, so this is just simply the product between the two. Okay, so this is a slightly more extensive model, and not used by Google, but nevertheless, there's many papers about it, and you know, we always think about new ways of improving the existing options. So the question now is, how can we find the optimal allocation? So before we had a simple sorting algorithm, and actually now we're going to start extending this model, and this is still a simple extension, and for this simple extension, we can still find a very efficient algorithm for finding the optimal allocation. Now, it's slightly different, so suppose, let's sort the ads according to the product, QI, VI, as before, and now we are going to allocate the top ad to the best position, meaning the position which has the highest viewing probability, and then the second best ad to the second best position, etc. Okay? So, in particular, if we have a decreasing situation where lambda j decreases in j, so the top position has a higher view probability, then the allocation actually exactly the same as before. Okay, so then there's nothing changing in the allocation, because the one with the QI VI we allocate, the highest QI VI we allocate to the top slot, and then the next one to the next lowest slot, etc., etc. So in terms of the allocation, nothing changes, but this is a more fine-grained model and allows us, you know, to say, okay, maybe there's a prominent page in the middle, or a prominent position in the middle of the page, which has a very high probability. So it's no longer allocating it from top to bottom, but more from most views to least views. Now, if we can look at the same problem as before, okay, and this could be, say, an exam question, for example. Suppose now that we have the same model as before, but we assume that we have an additional parameter, which is the probability that the person views the ad. And for example, we can take the top position to be 1 and the second highest position to be a half, right? So this question is a trick question. Okay? So compute an allocation, payment, and expect utility of winners in a GSP auction. Okay? Now, this is a trick question because the answer is the same as before, because the GSP auction does not take into consideration this lambda value. Okay. So it's different. Okay. Now, this one could be a different answer. Okay. Oh, actually, the expected utilities are now different, right? So let's have a look. So everything is the same except for the expected utilities, right? So here we had the expected utilities, right? But now the probability of actually being clicked also includes this position-dependent factor. Okay. Now advertiser 2 gets slot 1, so the position dependent was 1. Okay. But now for slot 2, the equality is 0.5. No, sorry, not equality. Lambda is 0.5. So now we have a utility of 0.1 only for the second slot. Okay. For bidder 3. Okay. Now let's have a look whether in this case, so if we look at the other part of the payment, okay, so is this auction truth-telling? Maybe in this case it could be. Okay. So let's have a look. So is this auction truth-telling? Well, let's have a look again. So if we now lower, so suppose that agent 2 now says, okay, I'm going to go have the second slot now instead of the first slot. Then the expect utility now is actually 0.5, because now the second slot has a kind of an extra discount factor, if you will, times what we already have calculated is 0.2. Okay? So in effect, now there's much less, there's no incentive anymore for him to manipulate the auction, because actually the second slot is not so valuable anymore. much less value. Yeah. So that's a slight modification. Now, if we compute the payments using the VCG mechanism, that could be another assignment. You can try that at home. Then again, we need to take into account the fact that actually the expect utility has changed now. So the social welfare also has changed. Okay, so if we want to compute the VCG payments, we also have to take into account this lambda value as well. Okay. So the VCG payments change. The GSP option payments don't change because GSP is GSP. GSP doesn't take into account lambda, but in the VCG mechanism, we can take into account a different model of the world. Now, this is still easy. Okay? And I don't have much time to do it in detail, but there's a very famous model in the literature, and we'll do that in more detail next time we meet on Thursday, and how you to conclude to these things. Now, here so far we've assumed, okay, that your click probability depends on two things. So the ad quality and the position that you're shown. In reality, the probability that a person scans below the first ad might depend on actually which ad is shown in the first place. Okay? So if you have various, say, coffee beans, right? You're going to click on the first one, and you might never actually end up in the second one. If the first one is no good, right? So you didn't like the coffee in the first one, you might go to the second one, right? So essentially, whether you scan to the next ad depends whether you clicked on the first one in the first place. So if the first one was already relevant, and you've clicked on it, then then the second one has less of a chance to be clicked, right? So this is a famous model. There's lots about it in literature. It's called the cascade model. So this cascade model is the idea that you first look at the first one. If you click on this, you're not going to go to the next one. If you didn't click on the first one, there might be a chance that you click on the second one. If you didn't click on the second one, you might go on to the third one, etc., etc. Okay. And so this is modeled by a kind of Markov. Well, we assume the users behave in a kind of Markovian way. You have like states, and the state of the user moves from one state to the next state, and there's a probability that the user moves from one state to the next state. So this is kind of a Markov model. Okay. So with the given probability, observe the next slot, and otherwise they stop browsing altogether. So how this is modeled is that each ad I has an individual continuation probability. So the continuation probability means, okay, given that I've seen ad 1, what's my probability that I'm going to continue to ad 2? So it could be that, so if Qi is the probability of clicking ad I, that probability of moving to the next one is 1 minus Qi, right? It could be, okay? But it could be less, right? It could be users already given up after seeing the first 3, they've given up. So it could be a completely different value, and to make it a bit more general, so we just have some sort of value Ci. Okay? So each ad is characterized now by 3 things. A Vi, the value, the quality of I, and continuation probability of I. Okay? So there's no maybe directly saying, okay, position 1 is this probability of being clicked, position 2 is this probability of being clicked. It depends on which other ads are shown above it. So what is the probability that a specific ad in a specific application is clicked? Well, we can calculate it like this. Okay? So suppose that we are in the jth position. So the probability that the ad in the jth position is clicked is equal to the quality of that ad times the continuation probabilities of all the ads above it. Okay? So we have, say, Q1 suppose these are shown in this order, right? So the probability that ad 1 is clicked is simply Q1. Okay? Now the probability that ad 2 is clicked is Q2 times the continuation probability, so this is not a, of C1, so times C1. And the probability that the third ad is clicked is Q3 times C1 times C2. Okay? So the one at the bottom has a increasingly lower probability of being clicked. So these are all values smaller equal to 1. Okay, these also. Okay. So this is the cascade model from the literature. Okay, so this is the most complex one we will discuss. They have even more complex models in the literature, but this is the most complex one we'll go for. And next week we kind of look at, okay, how do we compute the optimal allocation in this kind of situation through the cascade model? And there's an interesting theory we can use, a theorem, that we can say, okay, if we knew which slots we were going to allocate or which ads we were going to allocate, there's a theory which tells us in which order we need to show them, okay? And this according to this so-called index. We have to rank that. We'll go more detail on Thursday. But we still have to choose, even if we know which order to show them, that maximizes social welfare, we still have to decide, okay, we have more ads than slots, so which of the ads do we select? Do we select simply the ones with the highest kind of index? That's not true, okay? So we have to use a different approach, which is called the dynamic programming, to find the optimal solution. And I'll show you how that works on Thursday, okay? All right, so I think we've run out of time now. We'll continue Thursday. Okay, any questions? Okay, great. See you on Thursday. Don't forget the homework.